aromaticity. Last time we have discussed structure of benzene, stability of this ring and the effect of this stability on its chemical properties. Now, in today's lecture, we will discuss other aromatic compounds other than benzenoid compounds. We will see the structural features which make these compounds aromatic in nature, which includes discussion of Huckel's rule also, and then we will discuss anti-aromatic compounds which includes butadiene and octatetraene. Then we will discuss aromaticity of cyclopentadienyl anion and cycloheptatrienyl cation. Then we discuss nomenclature of benzene derivatives. Now, first we discuss other aromatic compounds other than benzenoid compounds. Now, first we take the properties, structural features which make these compounds aromatic in nature. So, what are the essential structural features that should be present in these compounds? These compounds should be cyclic and should contain conjugated pi bonds. Each atom in a ring should be sp2 hybridized and should contain one unhybridized p orbital. There should be an effective overlapping of p orbitals, and for this effective overlapping the structure must be planar. Then there should be a delocalization of 4n plus 2 pi electrons. For example, if n is 1, then total delocalization of 6 pi electron, and this delocalization should lower the energy of the system. And these type of compounds undergo electrophilic substitution reactions. In spite of having high pi electron density, these do not undergo electrophilic addition reactions like alkenes. Now, first we see why there is a need of 4n plus 2 pi electrons for a compound to be aromatic. This requirement, this is known as Huckel's rule, which is based on quantum mechanics. Here the delocalization of these 4n plus 2 pi electrons gives stability to the molecule. Further, it was found that if there is a delocalization of 4n pi electrons in a cyclic structure, that destabilizes the molecule. So, here 4n plus 2 stabilizes the molecule, and here 4n pi electron destabilizes the molecule, and these type of molecules are known as anti-aromatic compounds. Now, to understand the 4n plus 2 pi electrons, we first have to discuss, or we have to first know about the polygon rule. Now, according to this polygon rule, these molecular orbitals arrange in energy wise according to their cyclic system, and it has the same polygon shape as the compound with one vertex at the bottom, and the non-bonding line cuts horizontally the center of the polygon. For this, we discuss the example of benzene. We know benzene is a 4n plus 2 pi electron system where n is 1. So, there is a 6 p orbitals which degenerate to give rise to 6 new pi molecular orbitals, and we have now 6 pi electrons. This is the energy diagram for new molecular orbitals. The new molecular orbitals which get formed are pi 1, pi 2, pi 3, pi 4, pi 5 and pi 6, and the energy wise these are arranged in this fashion. This is the same hexagon which the benzene is having, and which with one vertex at the bottom, and in the center this non-bonding line is there. So, now filling of this molecular orbitals taking place according to Aufbau principle and Hund's rule. Now, there are 6 pi electrons. So, first 2 electrons goes in pi 1, then 2 electrons in pi 2, and then 2 electrons in pi 3. So, all bonding orbitals get filled up first. There is no electron in non-bonding, and all the electrons are paired in bonding. So, that is why the benzene structure is stable. Next example we take cyclobutadiene. Now experimentally it was found that heat of hydrogenation of cyclobutadiene is minus 91 kilocalorie per mole, which is more than the double of heat of hydrogenation of cyclobutene. That means this system is more energetic even than cyclobutene. Even though there is a delocalization of these two pi bonds, each carbon is sp2 hybrid, each carbon is having one unhybridized p orbital with one electron, but in benzene, as in we see in benzene, there is a stabilization by 36 kilocalorie per mole, but here the energy of this system is more. Now what is the reason? Again we consider there is a energy diagram of new molecular orbitals. So here 4 new molecular orbitals will be generated, pi 1, pi 2, pi 3 and pi 4, and filling of orbitals taking place, there are 4 pi electrons. So 2 pi electrons in pi 1, then pi 2 and pi 3, these are 2 non-bonding orbitals. So these two get 1 electron each. Now see here, these electrons are unpaired. So due to this unpairing of electron, this system get destabilizes, and that is the reason why this system is more energetic in spite of having delocalized pi electrons. We discuss one more example of cyclooctatetraene. Here again we see heat of hydrogenation should be 4 times of heat of hydrogenation of cyclooctene, which is minus 23 kilocalorie, but it is for cyclooctatetraene this energy is more than the 4 times. That means again this system is not stable. If we see the structure, here again it is a cyclic system having conjugated pi bonds, and there is a delocalization of these pi electrons, and it is a planar one. Now again we see this molecular orbital diagram energy wise. Now there are 8 p orbitals, so this gives new 8 molecular orbitals, and these 8 new molecular orbitals arrange in cyclooctane with one vertex at the bottom and non-bonding line in the middle. Now we have pi 1, pi 2, pi 3, pi 4, pi 5, pi 6, pi 7 and pi 8. So there are 8 pi electrons. So 2 pi electrons in pi 1, 2 in pi 2, 2 in pi 3. So all the bonding orbitals are filled, we are left with 2 electrons. So 2 electrons, 1 each in 2 non-bonding orbitals. Again here single electrons are present which are not paired. So that is why again due to this unpairing of electrons, the system is not stable. So we have seen cyclobutadiene and cyclooctatetraene are not stable in spite of having a delocalized pi electrons, but those system contains 4 and pi electrons, and reason is unpairing of electrons. Now we next take aromatic ions. First we take cyclopentadienyl anion. Now see here, this is a cyclopentane ring having 2 double bonds and a negative charge. So there is a each carbon here is again sp2 hybridized, and each carbon is having one unhybridized p orbital. 4 carbons are having 1 electron in each p orbit unhybridized p orbital, but 5th carbon, which is bearing a negative charge, having a pair of electron in its unhybridized p orbital. So in total there are 6 pi electrons present, which is a Huckel's number. So that is why this cyclopentadienyl anion is aromatic in nature. We can see here there is a overlapping of p orbitals, it is a planar structure, 2 electrons, 2, 3, 4, 5, 6. So there is a delocalization of 6 pi electrons, and we see here these resonating structures, and this is a resonance hybrid of cyclopentadienyl anion, and this also reflect in cyclopentadiene molecule also. it is very acidic in nature. Why? Because on losing proton it gives cyclopentadienyl anion, which is aromatic in nature and it is stable. So, that is why cyclopentadiene molecule is acidic in nature. Now, next ion we take cycloheptatrienyl cation, which is also known as tropylium ion. It is a 7 carbon chain. Again here we have a 3 conjugated double bonds with 1 positive charge, which is also in conjugation with this double bonds. So, now here we have 7 sp2 hybridized carbon atoms. 6 carbons are having 1 unhybridized p orbital with 1 electron each, while the 7th carbon, which one is bearing positive charge, having empty unhybridized p orbital. So, we are having a delocalization of 6 pi electrons over 7 carbons. So, this is a delocalization of p orbitals, and here you can see the resonating structures of this cycloheptatrienyl cation, and this is a resonance hybrid. So, again here there is a delocalization of 6 pi electrons, which is a Huckel's number, and that gives stability to the system, and this also reflects in tropylium bromide. Tropylium bromide as such is a organic compound, but it behaves like a ionic compound. It is having a high melting point. Why? Because tropylium ion is very stable. So, that is why it is a ionic compound more as compared to covalent. Now, we can discuss the aromaticity of following ions also. Now, first is cyclopropenium ion, which is a 3-membered cyclic ring. It is having a positive charge in conjugation with this double bond. So, each carbon is sp2 hybridized and each is having 1 unhybrid p orbital. These 2 p orbitals of these 2 carbons are having 1 electron each, and this p orbital is empty. So, there is a delocalization of this positive charge in this ring, and this delocalization involves 2 pi electrons, which is again a Huckel's number corresponding to n is equal to 0. So, this is also aromatic ion. Now, cyclopentadienyl cation, in this we have a 5-member cyclic compound, and this positive charge is in conjugation with these double bonds, but here again delocalization involves only 4 pi electrons. So, this is again anti-aromatic, not aromatic. Cycloheptatrienyl anion, here negative charge is in conjugation with this 3 pi double bonds. So, but here it is just like cyclooctatetraene, delocalization of 8 pi electrons. So, that is why it is also not a stable structure. So, this is again anti-aromatic. So, now we have discussed what are the different conditions which are required for a compound to be an aromatic. So, by applying those conditions, we can discuss the cyclic compounds with conjugated double bonds, whether these compounds are aromatic in nature or not. So, now next we will discuss the nomenclature of benzene derivatives. So, first monosubstituted benzene derivatives. These derivatives are named first by writing the name of substituent followed by the word benzene. For example, if bromine is attached to benzene, then this is known as bromobenzene. With chlorine, this is known as chlorobenzene. With nitro group, this is known as nitrobenzene. With ethyl group, this is known as ethyl benzene. Now, with the second type of nomenclature in these derivatives, mostly these are named according to their common names and not by IUPAC names. For example, if benzene ring is attached to OH group, then this is known as phenol, while its IUPAC is benzenol. With methyl group, methyl benzene, but this is known as toluene. With amino group, instead of benzenamine, this is known as aniline. With OCH3 group, this is known as anisole. not methoxybenzene. With COCH3 group, instead of methyl phenyl ketone, we call commonly as acetophenone. With CHO group, this is known as benzaldehyde. With COH group, this is known as benzoic acid. Now, if benzene ring is present as a substituent, then this is known as a phenyl group. For example, if this is present in this aliphatic chain, number 2 position, this is an alcohol, number 2 position, this benzene ring is present. So, this is known as 2-phenyl ethanol. If with benzene a CH2 group is also present, then this group is known as benzyl group. For example, this molecule is known as benzyl bromide. One more nomenclature, we can use AR. In general, this is a general term for a phenyl group or a substituted phenyl group. For example, for phenols, normally we can use AROH. This is a substituted phenol having Br, this is having CH3 and this is unsubstituted phenol. But all these we can simply write for all these AROH. AR means aryl, which is common for all these substituted benzene ring. Now, for di-substituted benzenes, these are named according to the prefix ortho, meta and para, which specify the substitution pattern. For example, if substitutions are present on 1 and 2 position, for example, chlorine on 1,2 position, then this is known as ortho dichlorobenzene. If the substituents are present at 1,3 dichlorobenzene, so this is called as meta dichlorobenzene. If substituents are present at 1 and 4, then this is known as para dichlorobenzene. If we have more than 2 substituents in the benzene ring, then we simply give numbering to the benzene ring and give the number to the substituents which are present according to the positions. For example, 2,4,6 tribromoaniline means at number 1 position NH2 group is present and number 2, 4 and 6 bromine atoms are present. Another example we can take 2,4-dinitrotoluene. In that case, number 1 position methyl group is present and number 2 and 4 nitro groups are present. So, this is the nomenclature of benzene. So, what we have discussed today? We have discussed today structural features which are needed for a compound to be an aromatic compound. We discussed the aromaticity of other compounds which are not benzenoid in nature, and we discuss also anti-aromatic compounds and how to name different benzene compounds. In the next lecture, we will discuss the electrophilic substitution reactions of benzene with their mechanism, that is, we will discuss how electrophiles get generated and how this electrophile get attack the benzene ring, and then how we get back the benzene structure back after substitution. Thank you.